amplifier. We have finished BJT and FET successfully. We have so I hope all your doubts are clear now. Okay, so let's start with the operational amplifier. This is the third unit. We have covered diode circuits and BJT FET. The operational amplifier, will see what is the operational amplifier and then we'll switch to the application of it. And the fourth unit will be negative feedback, or we'll see the feedback over here, and oscillators, and apart from this, power amplifiers also. Okay friends, so what are the objectives for this unit? I'm sorry. To know about the differential amplifier, to introduce operational amplifier, and all related to amplifiers, right? Let's come to the topic now. I'm sorry. So the introduction, what is the operational amplifier? Actually friends, the operational amplifier is a direct coupled high gain amplifier. Direct couple means it's directly given like this. You have to apply input over here and you have to take output. If this is V1, this is V2, you are applying over here. Here directly you are getting output. Your difference of this will be multiplied with AD, where AD is the differential gain. Okay, so this is we called Opamp. What Opamp do? Opamp take the difference of input stages, because inside of this we are having differential amplifiers. Okay, so Opamp is based on differential amplifiers only. Inside of the Opamp we are having differential amplifiers. So the input V1 and V2 will come with difference at the output. So V0 will be like A is the gain of this, multiply with V1 minus V2, input differences. Okay, so later we'll discuss about this symbol. Let's come here. Oh, wait a minute. So the operational amplifier is a direct coupled high gain. The gain is very high amplifier, usable from 0 to 1 megahertz. For very high frequency it can work, to which feedback is added to control its overall response and characteristics. Means we can add the feedback also. This will be the circuit in which not only you are having input and output set, but you have the feedback also from the output. You can apply your feedback to either of these two input voltages or terminals. Is it okay friends? So such direct coupled DC amplifiers do not use blocking, coupling and bypass. See, there in the BJT circuits we were using some coupling capacitors, right? At the output stage we were using to eliminate the DC. At the input stage we were using to add the DC, like this. In this nothing is there, just you have to apply V1 and V2 on two of the terminals and you have to get the output. So the such direct coupled DC amplifiers do not use blocking capacitors, since this would reduce the amplification to zero at zero frequency. Okay, large bypass capacitor may be used, but it is not possible to fabricate large capacitors on a IC chip. Okay, so the capacitors fabricated are usually less than 20 picofarad. Transistor, diodes and resistors are also fabricated on the same chip. So we are introducing this Opamp in IC chip. Okay. So this is the building block of Opamp. So first we'll discuss about the differential amplifier. This is kind of BJT circuitry is given over here, and then we'll switch to the Opamp circuit. Differential amplifier is a basic building block of an Opamp. This is the operational amplifier. The short name of operational amplifier is Opamp. So differential amplifier is the basic building block of the Opamp. The function of a differential amplifier is to amplify the difference between two input signals. Okay friends, forget about this circuit. Okay, till now you have seen only this thing, right? Here we were applying some, we were taking output we were applying some input. If you have given AC circuit, you are taking the same AC at the output. This will be the amplified version. Okay, but in the differential amplifier, what is the new? In the differential amplifier, you are not taking only one input. You are taking two inputs and then you are differentiating them. Means you are taking difference at the output stage. So now come to the point. The two transistors Q1 and Q2, you can see over here, this is Q1 and this is Q2, have identical characteristics. Both are identical, means every parameters and elements connected to these two circuits are same, whether it's RC1, RC2, RE1, RE2, minus VEE, minus VE, and VC, VC. Okay. So the two transistors Q1 and Q2 have identical characteristics. The resistances of the circuits are equal. Means RE1 is equal to RE2. These both are equal, but equal to RC2 also. Means all are same values. And the magnitude of plus VCC is equal to the magnitude of VEE, though we are applying VEE negative and VCC positive. But the magnitude of both of them are same. So these voltages are measured with respect to ground, and with respect to ground, the value of these voltages are given. Okay. So when you will combine this circuit will become like this. VCC is common because the same value. VEE is also common, same value. Now your task is to connect ammeter to emitter. So these two things will become in parallel combination. So this RE is the parallel of these two. Is it okay? So in this RE, now the current will be 2IE. 2 times of IE. One is from this side, one is from this side. Is it okay? And here we are taking output. At the collector terminal, we always take the output, and we are taking output like this way. We are considering terminal A and terminal B. A belongs to Q1, B belongs to Q2. And here we'll take the difference of outputs. Is it okay? This is differential amplifier. So, to make a differential amplifier, the two circuits are connected as shown in the figure we have seen earlier. The two plus VCC and minus VEE supply terminal are made common. Yes, we have done this. Because they are same. Okay. The two emitters are also connected, and the parallel combination of RE1 and RE2, they are connected in parallel, is replaced by a resistance RE. Okay, fine. The two input signals V1 and V2, these are the input signals. You can see over here, input signals V1 and V2. So two input signals V1 and V2 are applied at the base of Q1 and at the base of Q2. So the output voltage is taken between two collectors. Yes, we have seen. The collector resistances are equal and therefore denoted by RC equal to RC1 equal to RC2. So this both RC1 and RC2 are same. Okay. So I hope its circuitry is clear. Okay. Now let's come to next point. Wait a minute. So ideally the output voltage is 0 when the two inputs are equal. Yes, it will be, because see, inputs are same, circuit parameters are same. So definitely the difference in output will be same. Suppose at Q1 you are getting 5 volt as the output. At Q2 you are getting 5 volt as the output. But what we are taking difference of them, means VQ1 minus VQ2 we are taking. So it will be 5 minus 5 equal to 0. But it will be 0 ideally. Practically it will not be 0. Okay. Because it is not possible to take two exactly identical BJT circuits. There will be some difference. Okay. So ideally the output voltage is 0 when the two inputs are equal. When V1 is greater than V2, the output voltage with the polarity shown appears. See, if V1 is greater over here, so definitely the polarity will be given in this way only. See, V1 is greater, so output is like VQ1. This time you are getting suppose 6 volt because V1 is greater. And here you are getting VQ2 is 5 volt. So definitely who is the higher potential? this one is the higher potential. The polarity will be like this. But what if V2 is greater than V1? If V2 is greater than V1, then polarity will change and positive will come this side and negative will come to this side. I hope it's clear to you, right? When V1 is less than V2, the output voltage has the opposite polarity. I think it's clear to you. Now let's come to next. So the differential amplifier of different configuration. We'll see the different configuration of the differential amplifier. Mainly we have the 4 differential amplifier configuration. The first one is dual input and balanced output differential amplifier. We'll see what is dual input and what is balanced output in the next slide. The second will be dual input and unbalanced output. Third will be single input and balanced output. Fourth one will be single input and unbalanced output. This dual input, sometimes we call it double tone. Okay. And for the single input, sometimes we call single tone circuit. Is it okay? Come to the next. Let me change the color now. So in the next point you can see these are the circuitry given over here. In this we have chosen V1, V2 and everything is same. So the first one is, we have seen the first one is dual input balanced output. Dual input and balanced output. So input are dual, double tone means at both transistors we are applying the input, and balanced output. Here the outputs we are taking at both the terminals. Okay, let me check the single one. So this is clear to you? Wait a minute. Later I'll show you what is the unbalanced output. Okay, double input is okay. You are applying V1 and V2, means you are applying V1 at Q1 and V2 at Q2. Now if we'll talk about the single input or single tone circuit, circuit will be like, wait a minute. Circuit will be like this. See, you can see over here. In this circuit, the input is applied at one of the transistors only, Q1, and the second input of the second transistor is 0. So this is the single output, and in the single output we have, so now the problem is what is balanced output and what is unbalanced output. So forget about this second circuit. You are having only this circuit and this circuit. So this circuit is single input, this circuit is also single input, but this circuit is balanced output. Means if you are considering the output as the difference of the both of the transistors, so we call it the balanced. But if you are taking output at only one stage, forget about this circuit. These two circuits are the circuits. Wait. So this circuit is balanced circuit and this is unbalanced circuit. Unbalanced means you are taking output at one of the transistors. Is it okay? Now, so this configuration are shown in figure and are defined by number of input signals used and the way an output is measured. If used 2 input signal, the configuration is said to be dual input. Otherwise, it is a single input configuration. On the other hand, if the output voltage is measured between 2 collectors, it is refers to a balanced output because both the collectors are at the same time DC potential with respect to ground. If the output is measured at one of the collectors with respect to ground, the configuration is called the unbalanced output. I think this point is clear to you. Okay. Now differential amplifier C. This is the exact circuit for differential amplifier. We connected collectors and we connected the ammeters V1 and V2. Okay, RS1, RS2, Q1 and Q2. A dual input balanced output difference amplifier circuit, it is shown in figure C. This is the balanced output. Why? Because I'm taking output in between 2 circuits. Okay. Now inverting and non-inverting inputs. What are the inverting and non-inverting inputs? In differential amplifier, the output voltage V0 is given by V0 is AD into V1 minus V2. It's definitely, we are sure that we are getting the difference of two inputs. Difference or C. In other words, you can take, because of this V1, both are identical. At this point, you are getting AD of V1. Is it okay? AD is the gain due to this circuit or amplifying factor. This is the amplification. And here I am getting AD V2. Now we are taking the difference of these. So V0 is automatically AD V1 minus AD V2. If you will take AD common over here, you will get V1 minus V2. The same thing is written over here. Is it okay? Like this. Now, the conditions. When V2 is 0, V0 is AD V1. Okay, fine. So this is the condition for singleton. Okay. When V1 is 0, suppose V1 is 0. This one is 0. Now your output by this equation will be minus AD V2. So this is inverting. Okay. Is it okay? So I can say this is non-inverting terminal and this is inverting inputs. Okay. So therefore the input voltage V1 is called the non-inverting input, because while considering V1 at a time, we are getting AdV1. Whatever input sign is there, we are getting at the output. So this is non-inverting. Okay. So the point is, therefore the input voltage V1 is called the non-inverting input because a positive voltage V1 acting alone produces a positive output voltage V0. Similarly, the positive voltage V2 acting alone produces a negative output voltage. Hence, V2 is called the inverting input. Okay, we have seen over here. Consequently, B1 is called the non-inverting input terminal and B2 is called the inverting input terminal. I think it's clear to you. Okay, this is B1 and this is B2. Correct? So now in the differential amplifier itself, we have common mode gain. But before that, I would like to tell you one more thing. If this is the circuit given over here, there will be some voltage gain also. ED will be output whatever. See, the formula is like this. AD will be V0 divided by V1 minus V2. So here also we'll study AC and DC analysis. AC and DC analysis. Okay. So I'm not going to analyze this circuit by these two parameters AC and DC. Directly I'm giving you formulas. So please note down. Okay. So directly I'm giving you formulas. Please note down. For AD, the voltage gain of differential amplifier is given by minus GM RC by 2. This is for double tone, okay? For double tone inputs. Minus GM RC by 2. Where what is the GM? You know very well. It is 1 by RE, okay? Into RC by 2. RC is the output, collector terminal resistor. Is it okay? RE you have to calculate. How to calculate RE? By VT divided by IC/DC, if you remember. And just reciprocal of it is nothing but GM we have seen over there. So formula AD is, again I'm telling you, GM RC by 2. Okay. And one more common mode is also there. And so common mode value will be minus RC by 2RE. RC is the output resistor and this is the input resistor, and we are taking 2 times. Is it okay? Now we'll see the CMRR formula also. Before that, let's know about what is CMRR. Common mode gain. Common mode gain AC. ACM, let's take it. And ACM, we have seen the formula, that is minus RC divided by 2RE. Is it okay? And differential gain formula we have seen is minus GM RC by 2. These are the very important formulas for differential amplifier. So a common mode signal is one that drives both inputs of a differential amplifier equally. The common mode signal is interference, static static and other kinds of undesirable pickup, etc. Common mode means, suppose due to this V1, you are applied V1 into the circuit, but some obstacle or some offset is also coming in the picture. Means some errors I can say, or unnecessarily, undesirable pickups are also coming. So at this stage, output will be ADV1 plus that undesirable into this signal again. So this is undesirable gain also coming into the picture. This is unnecessarily, and practically this value is very low actually. Very low. Okay, so this is common mode gain. Let's see. Wait a minute. See, a common mode signal is one that drives both inputs of a differential amplifier equally. So at both inputs we are getting this common mode gain, or the output due to this common mode gain. So the common mode signal is interference, static and other kinds of undesirable pickups, etc. If V1 and V2 are two input signals, then the output of a practical op-amp can't be described by simply we are taking this. For any op-amp, the output we are taking V0 is nothing but differential gain multiply with difference of input. But this is not only for the practical. We are getting something else. Output will be this. This will be our output. So our output V0 will be AD VD plus AC VC. This is the common mode gain. This is the differential gain. This is the difference of inputs. This will be average of the inputs. Okay. So V1 equal to this VC plus half of VD, and V2 equal to VC minus half of VD. So substituting V1 and V2 in output voltage, so you will get this one. A1 VC plus half of VD plus A2 VC minus half of VD. So half A1 minus A2 into VD, and like this. So what finally we are getting is, ADVD plus AC VC. This is the output. Okay. Actually this VC is the average of these two. VC is actually V1 plus V2 by 2. Okay. If you'll put these values, then you will get automatically this. How we get the V1? This is given over here, right? So V0 is like this. So the voltage gain for the differential signal is AD, and for the common mode is AC. Perfectly fine. So remember like this, if this is your op-amp, so the gain of this op-amp is not only AD but AC also. Two types of gain. This is unnecessarily undesirable gain. Okay. The ability of a differential amplifier to reject a common mode signal is expressed by its common mode rejection ratio. So see, here is the beauty of differential amplifier. We can see what differential amplifiers do. At the input V1, at the output V2, the same amount of undesirable pickups are coming, suppose. Okay. So let's X is coming. Here also X is coming. But at the output stage, we are taking V0 equal to AD, and difference of this V1 plus X minus V2 minus X. So X will cancel out. So noise will be filtered out by this differential amplifier. Okay. But practically we are having a very, low amount of offset. So the ability of differential amplifier to reject a common mode signal is expressed by its common mode rejection ratio, CMRR, common mode rejection ratio, given by the ratio of AD and AC. AD divided by AC is nothing but the CMRR. Okay, so practically or ideally the CMRR for any op-amp should be infinity. Why? Because we need AC equal to 0. So it will be infinity. So ideally the CMRR should be infinity. Okay. So it is the ratio of the differential gain AD to common mode gain AC. I hope it's clear to you. Right? So the formula is AD divided by AC. Correct? Now let's come to the operational amplifier. Now this is the starting of operational amplifier. We have seen the building block of operational amplifier, and that is differential amplifier. Now we are switching to the operational amplifier. An operational amplifier is a direct couple high gain amplifier, okay, consisting of one or more differential Opamp amplifiers and followed by a level translator and an output stage. An operational amplifier is available as a single integrated circuit package. In a single circuit, single AC chip, we are available with operational amplifier. Okay, so this is the inside story. Okay, what you are applying two inputs. This is non-inverting terminal, means this is the positive and this is the negative, so it is inverting, and at the output you are getting difference AD V1 minus V2. I hope it's clear to you. Okay, so inside of the Opamp, this is not the important part, but we have to check it. It's input stage. Here we are going to apply the inputs. This is the intermediate stage, and here we'll set the level, and this is the output stage. Okay, so wait a minute, I'm sorry. The input stage is a dual input balanced output differential amplifier. See, the input stage of operational amplifier is dual input because we are applying two inputs, and balanced output. Okay, this stage provides most of the voltage gain of the amplifier and also establishes the input resistance of the Opamp. Yes, Opamp input resistance will be very high. The intermediate stage of Opamp is another differential amplifier which is driven by the output of the first stage. The first stage output will drive to second circuit. Okay, this is usually dual input unbalanced output. Here at this stage you will be having surely dual input and balanced output, but here you will be having unbalanced output. Is it okay? Now let's come over here. Because direct coupling is used, the DC voltage level at the output of intermediate stage is well above ground potential. Okay, we have seen the level shifter, right? So therefore level shifting circuit is used to shift the DC level at the output downward to 0. Means we are adding some DC part to the signal. At the output we have to remove that DC part. We are not using over here the capacitor. So that is the entire circuit we have given the name, and the name we have given is, wait a minute, some problem is there, wait. So because direct coupling is used, the DC voltage level at the output of intermediate stage is well above the ground potential, and therefore the level shifting circuit is used to shift the DC level at the output downward to 0 with respect to ground. Okay, the output stage is generally a push-pull complementary amplifier. The output stage increases the output voltage swing and raises the current supplying capability of the Opamp. It is also provides low output resistance. The low output resistance means which type of source it is. This is voltage source. At output it is voltage source. At input this is the voltage control voltage source. Is it okay? Voltage control voltage source, if you remember, we have seen the output will be 0 and input will be infinity ideally. Okay, practically it's very high, it's very low. Okay, fine, perfectly fine. Come to the next. This is the symbol of Opamp. The symbolic diagram of an Opamp is shown in the figure. See over here you can see a very beautiful symbol for that complicated inside circuit, differential amplifiers and so many things. Input, two inputs, Inverting inputs means definitely it will be minus. Non-inverting, definitely it will be plus. Plus VCC, this is the, working potential given to the, working voltage given to the op-amp. We are taking output V0 and that is the gain of this A into V1 minus V2. I hope it's clear to you. Okay, now we'll see some op-amp parameters now, and then we'll see some strategy related to op-amp circuit. I mean, we'll see the feedback, open loop and closed loop and something. So let's come to the parameter now. The parameters of op-amp. So first and very most is input offset voltage. Offset means error, okay, undesirable quantity. So input offset voltage. See, due to this circuit we are having some input voltage, unnecessary voltage. We are using some, inside the BJT circuitry and all, some potential 0.7. Suppose for the BJT we have VBE is like 0.7. So this is undesirable at the output stage. So this one of the example I'm showing you. Like this we are having some input offset voltages. So see, in the offset voltage, input offset voltage is defined as the voltage that must be applied between the two input terminals of an op-amp to null or zero the output. Is it okay? Shows that two DC voltages are applied to input terminal to make the output zero. Here, suppose we are applying this by outside means VDC and VDC2. So we are getting at the output VDC1 and VDC2. So effect of undesirable signal should be nullified. Okay. So VIO is nothing but VDC1 minus VDC2. So VDC1 and VDC2 are DC voltages and RS represents the source resistance. Okay, this is the RS source resistance. VIO is the difference of VDC1 and VDC2. It may be positive or negative. Okay. So let's come to the point input offset current. Input offset voltage is clear to you. These are the input offset voltages, means we have to nullify them. Output of these two should be 0, or at this stage you can take it, it's error. At terminal 2 also it is error, and because of this beauty of operational amplifier we need to make it 0. The effect of this 2 is 0. Okay. So input offset current, let's come to the second parameter, that is the input offset current. The input offset current IIO is the difference between the currents into inverting and non-inverting terminals of a balanced amplifier. See, the input offset current we are talking about. In the positive terminal, or I'll say it non-inverting terminal, the current given is IB1. Here the current is IB2. So the difference IIO in input offset current is difference of this IB1 minus IB2. Is it okay to you? So let's come over here. IIO is given by the mode of, we are considering only magnitude, IB1 minus IB2. Okay. So this is the input offset current. Now input bias current. What is the bias current? The input bias current IB is the average of the currents entering the input terminals. If I'll talk about the input bias current, so what I have to do is I have to take the average IB1 plus IB2 divide by 2. Is it okay? And input offset current if I have to talk about, so I have to take difference IB1 minus IB2. Is it okay? So the input bias current IB is the average of the current entering the input terminals of a balanced amplifier, that is this. Differential input resistance. What is the resistance you are getting at the input stage of op-amp? This is kind of thing. This is V1. Let's take it V2 plus and minus. What is resistance offered by this op-amp? And we discussed earlier the op-amp resistance, input resistance is very high in mega ohms. Is it okay? So Ri is the equivalent resistance that can be measured at either the inverting or non-inverting input terminal with the other terminal is grounded. Okay, so in generally it's 1000 giga ohms, very high, it's giga ohm. Okay, input capacitance. What is the input capacitance? So Ci is the equivalent capacitance that can be measured at either the inverting and non-inverting terminal. It offers some capacitance also, because inside some BJT circuitry is there, right? We are having two junctions, so definitely we are having some capacitance also. So if we'll talk about the operational amplifier, we can't exclude this capacitance. Okay. Let's come to the next. That is the input voltage range. What will be the input voltage range? See, input voltage range is the range of the common mode input signal for which a differential amplifier remains linear. It is used to determine the degree of matching between the inverting and non-inverting input terminals. So the range of input, see friends, the range of input is, if this is your op-amp, here I am taking output, here I have to apply inputs V1 and V2. The gain of this is 10 to the power 6. This is the working voltage you are giving to it. So your output can't exclude to this, means you can't go beyond this 15. So 15 divided by 10 to the power 6. This is the minimum voltage you can apply over here. So minus 15 10 to the power 6 to 10 to plus 15 10 to the power 6. This is your input range. Okay. Now the most important thing is the common mode rejection ratio we have seen earlier. The CMRR is defined as the ratio of the differential voltage gain AD to the common mode voltage gain ACM. We have seen it. Okay. Supply voltage rejection ratio. Supply voltage rejection ratio. SVRR is the ratio of the change in the input offset voltage to the corresponding change in the power supply voltage. This is expressed in millivolt or in decibels. SVRR, see, this is the ratio, right? So in millivolts divided by volts we are taking this, or in decibels also we can convert. So SVRR can be defined as this: difference in input offset voltage divided by dV. Okay, corresponding change in the power supply voltage. Now come to the large signal voltage gain. Since the op-amp amplifies a difference voltage between two input terminals, so the voltage gain of the amplifier is defined as the large signal voltage gain. A is nothing but V0 by Vd, output voltage divided by differential input voltage. So this is nothing but AD we are talking about, V0 divided by V1 minus V2. This is the large signal voltage gain. The range of this is 10 to the power 6 to 10 to the power 8. Okay, so that's why I'm saying this very large. Let's come to the output resistance. As we discussed earlier, op-amp is voltage control voltage source. Voltage source means output should be 0, or in practical it's very minimum or very low, and at the input if we'll talk about, it should be infinity. So R0 is the equivalent resistance that can be measured between the output terminals of the op-amp and the ground. So everything will be measured with respect to ground only. What is the power consumption? The power consumption is the amount of Q power V in equal to 0 that must be consumed by op-amp in order to operate properly. Is it okay? The amount of power consumed by it's very low, 85 milliwatt. The power consumption by the op-amp is 85 milliwatt. Okay. So this is the power consumption. Consider when input is 0. When input is 0 and you are applying your bias potential plus 15 and minus 15. So whatever the power is taken by this circuit is nothing but 85 milliwatt. Okay. Let's come to the gain and bandwidth product. So gain n, I think it's wrong. Over here it's 13, 14 and this is 15. Gain bandwidth product. Gain and bandwidth. It's very important point as far the Opamp is concerned. Okay. So the gain bandwidth product is the bandwidth of Opamp when the open loop voltage gain is reduced to 1. See what they are saying. The bandwidth of Opamp. The gain bandwidth product is the bandwidth of the Opamp when the Opamp loop voltage gain is reduced to 1. If gain will become 1, so gain bandwidth product will be equivalent to bandwidth or not. This is the figure 6. Okay. From open loop gain versus frequency graph at 1 megahertz shown in the figure. This is the frequency 1 mega. And this is gain over here. Okay. So it can be found that 1 megahertz for this IC Opamp frequency, the gain reduced to 1. Here the gain reduced to 1. This is show the gain 1. So when gain become 1, that frequency is the bandwidth. The mid band voltage gain is 10 to the power 5 and cutoff frequency is 10 Hertz. Okay. Slew rate. This one is very important. Slew rate. The slew rate is defined as the maximum rate of change of output voltage per unit of time under large signal conditions, and it is expressed in volts per. Means the change in output with respect to time. Is it okay? Slew rate is given. Change in the output means dV naught by dt and measured in voltage per microsecond. Is it okay to you? So we are considering the change in output. How the output is changing. Okay. Now come to the ideal Opamp. If your Opamp is ideal, you are taking, wait a minute. V1, V2 and V0 plus minus. If this is the ideal Opamp, then the differential gain, let me change the pen, differential gain AD is infinity. What about CMRR? CMRR should be infinity. What about slew rate? Slew rate is dV0 by dt. See, with the minimum time there will be change in output. Means your circuit should be very fast. The input is, you applied the input and suddenly the output should change. So in the 0 time the output should change. So 1 by 0 again it is also infinity. What about R in? The input resistance. Input resistance should be very high. Again it's infinity. Okay. What about bandwidth? Bandwidth is very high. We have seen in mega. So it is also infinity. Is it okay to you? Now if I'll talk about R0, R0 should be 0. What about noise? Absolutely, noise should be 0. Is it okay? So, infinite voltage AD equal to infinite, we have seen. Infinite input resistance Ri, so that the almost any signal source can drive it, and therefore is no loading of the input source, no loading effect. See, if input resistance is very high like infinity, whatever input you will apply over here, the entire voltage will come at that point. If this is not infinity, so some voltage drop will be there, and the voltage drop because of low resistance called the loading effect. So your Opamp should be free from loading effect. Zero output resistance R0, so that the output can drive an infinite number of other devices. Is it okay? The output can drive an infinite number of other devices because the output is 0. No drop will be there. Zero output voltage when input voltage is 0. Zero output voltage when the input voltage, definitely if input voltage is 0, V0 should be 0. There should be no offset inside. Infinite bandwidth. the bandwidth should be infinite so that the frequency signal from 0 to infinite hertz can be amplified without attenuation. Bandwidth high means it can take large signal at input. Okay, high frequency signal at the input, and output also it can easily amplify the large signal or large frequency signal. So bandwidth should be high. Infinite common mode rejection ratio, we have seen CMRR should be infinity. Why it should be infinity? Because this is AD by AC. AC should be 0. So CMRR should be infinity. Infinite slew rate, so that the output voltage changes occur simultaneously with input voltage changes. What it means? You applied input. Suppose this is your input. Now at this point 0, it's change. Your input is constant up to this point t equal to 1, but at t equal to 1 it's changing suddenly. So immediately your output should change, right? This is your output, so immediately your output change at t1. Otherwise, if t1 is high, so your output will go continue and it will change after some time. So this is error kind of thing, or attenuation to the waveform. So the time should be 0. At minimum time, the change in output should be very high. The slew rate should be means infinity. Is it okay? Now let's come the equivalent circuit of the Opamp. This is inside of the Opamp. Equivalent circuit shows an equivalent circuit of an Opamp. V1 and V2 are the two input voltage. Here the V1 and V2 are the two input voltages. R1, Ri is the input impedance of the Opamp. This is the Ri. Ri should be infinity or very high. And AD VD is an equivalent Thevenin voltage across an R0. This is the R0. R0 is connected with the equivalent voltage of the circuit AD VD. Okay, R0. So R0 should be very low, means there should be no drop over here. So the Thevenin voltage source, and R0 is the Thevenin equivalent impedance looking back into the terminal of an Opamp. Is it okay to you? If I'll show this circuit, it will be looking like, suppose if we are doing this ground, so it will be V1. At the input stage, it's open circuit. So here it's VD only. See, this is the VD. I'm taking like this. And over here, plus minus AVD. Here it's R0. This is your circuit. Here you can take the output V0 by applying some resistor over here. Okay, this is your equivalent circuit of the Opamp. Let's come to the next. This equivalent circuit is useful in analyzing the basic operating principles of Opamp and observing the effects of standard feedback arrangements. In the next video, we'll see some feedback arrangements for Opamp also. So V0 is AD V1 minus V2. The output will be differential gain multiplied with difference in input. Now open loop Opamp configuration. Open loop. Open loop means there is a no feedback from output. This is V0, Vi and V2 plus minus. There is a no feedback from, so this is not self-controlled. In this case, in the case of amplifiers, the term open loop indicates that no connection exists between input and output terminals of any type. That is, the output signal is not fed back in any form as a part of the input signal. There is no connection between output and input. So feedback is 0. In open loop configuration, the Opamp functions as a high gain amplifier. There are 3 open loop Opamps configuration. Okay, and they are The open loop configuration, the Opamp function is a high gain amplifier, and there are 3 open loop Opamp configurations. Okay. The differential amplifier by Opamp. See, this is the open circuit. There is no feedback from the output, but it will differentiate two inputs. V1 I applied over here, V2 I applied over here. These are the input resistances over here, and VD is the difference between V1 and V2. We are multiplying this VD by AD and getting output, where AD will be V I in minus V in 2. Since the Opamp amplifies the difference between the two input signals, this configuration is called the differential amplifier. The Opamp amplifies both AC and DC input signals. The source resistance R in 1 and R in 2 are normally negligible compared to the input resistance Ri. Therefore, here is the input resistance for this Ri. Okay. Therefore, voltage drop across these resistances can be assumed to be 0. We don't have any resistance over here. The situation is like this. Therefore, V1 is Vn1 and V2 is Vn2. And output is AD Vin1 minus Vin2, where AD is the open loop gain. I think it's clear to you. Okay. Now, the inverting amplifier. What is the inverting amplifier? Inverting amplifier means your input will be at inverting terminal only. Non-inverting terminal will be directly connected to the ground. So at the output, you will get the 180 degree phase shift. That's why we are calling it the inverting amplifier, means the amplifier who are going to invert the input signal. If input signal over here is like this, at the output, I'll get like this. Is it okay? So V1 is 0 over here, V2 is V1, Vin applied at the inverting terminal. So V0 will be minus AD into Vin. The negative sign indicates that the output voltage is out of the phase with respect to input by 180 degree or opposite in polarity. Thus the input signal is amplified and inverted also. I hope the point is clear. Let's come to the non-inverting amplifier. This is non-inverting amplifier. In the non-inverting amplifier, you will apply the input to the non-inverting terminal, and the inverting terminal will be directly connected to the ground. Here also this R in should be 0, R in 1 actually, and the Opamp R in is over here given, and this R in should be infinity. So entire input you can take over here. Here the difference will be V in minus 0. V in 1 minus 0. Okay. V in or V1 is the V in, V2 is 0. So this is the output. So this is the non-inverting output. Okay. So this means that the input voltage is amplified by AD and there is a no phase reversal at the output. Let's come to the next. The gain of Opamp can be controlled if feedback is introduced in the circuit. Okay. So feedback is mainly to control the input, okay, or to control the gain. Input is fixed. If you want to control the gain of the system, you need to feedback it, okay. Control if feedback is introduced in the circuit. That is, an output signal is feedback to the input either directly or via another network. If the signal feedback is of opposite or out of phase by 180 degree with respect to the input signal, the feedback is called the negative feedback. Is it okay? An amplifier with negative feedback has a self-correcting ability of change in output voltage caused by change in environmental conditions. It is also known as the degenerative feedback because it reduces the output voltage and in turn reduces the voltage gain. Negative feedback is very, very, very important. Okay. Very important. Negative feedback. And we are using this feedback only. Though negative feedback reduces the gain also. But it eliminates the error. Whatever errors are coming, environmental error, the negative feedback is going to correct them. And negative feedback will be like If this is positive terminal, this is negative terminal, the feedback will come from output to negative terminal. The situation is like this. This is the negative feedback. Let's take parameter beta. Is it okay? So an amplifier with negative feedback has a self-correcting ability. It will correct by itself if voltage V0 will change by some means. So at the input stage, automatically the signal will go over here and the Opamp will adjust the input over here and it will correct itself. Okay. If the signal is fed back in phase with the input signal, the feedback is called the positive feedback, and in positive feedback, the feedback signal aids the input signal. It is also known as the regenerative feedback. Positive feedback is necessary in oscillator circuit. In oscillator circuits. Okay. Now see, this is the biggest advantage of negative feedback. In the negative feedback, it stabilizes the gain. We need a stable gain for any process. So negative feedback is very important. Increases the bandwidth, and you know for the Opamp the bandwidth should be infinity, very high. So negative feedback is going to increase that. So again it's very useful. The input and output resistances. Other benefits are reduced distortion, reducing the distortion, and reduced offset output voltage. It also reduces the effect of temperature and supply voltage variation on the output of an Opamp circuit. So for the Opamp, suppose this is the output, here is the input, here is the two inputs V1 and V2. This is V0. And V0 is coming with some errors. So one fellow is given over here, that is negative feedback. It will eliminate all these things and you will be having pure output V0 or controlled output. Okay, this is the, you can understand by this example. So friends, this is all about today's class. We'll meet in the next with the problems of Opamp circuit. And Opamp circuit is very important because in the gate examination, if you'll see the analog circuit, 70% they're asking from Opamp circuit only. Okay, we'll meet in the next. Till then, take care and bye.